Okay, this just in. Just got this email 10 minutes ago. Results from your exam yesterday. So every asterisk up there is a person, okay? So somewhere you're in that list somewhere, okay? So I'll crunch the numbers today or tomorrow, and I'll put an announcement on Blackboard so you can go find your raw score and figure out what your score out of 100 was on this exam, and then we'll go over some of the most problematic items on Monday, okay? Congratulations, one person got them all right. Right there. It wasn't you, Alex. Okay. All right, so polynomial. So this is just a review of polynomials. What is it? It's the sum of monomials. So it's x to a whole number. X to some whole number. So you can't have x to the 1/2, or you can't have... All right, can we start? We're going to start, okay? If you need to get your notebook out, that's fine, just do so quietly. So the powers of x can be whole values only, not decimals, not fractions, not negatives. Okay? But then the coefficients can be any real numbers. Negative, decimal, irrational, fraction. Okay? And we saw two different forms. The expanded form is where that's kind of the traditional standard form of sum of monomials, but then you can also write it, some of them can be written as a product of their factors. And we worked on how both those forms helped us to create the graph and understand what's going on with a particular function. So now we're going to talk today about what's called rational functions. So a rational function has the word ratio in it. So that ratio is talking about what kind of function it is. It's the ratio of polynomials. So we take one polynomial and another one, and we make a big fraction out of it, and this creates what's called a rational function. So we'll use nx here to mean the numerator. That polynomial that's in the numerator, and d would be the polynomial that's in the denominator. So let's talk about, so all this stuff that we learned about polynomials is going to be really important for understanding rational functions. So all those same principles, for the most part, apply, and we'll see that. So let's talk about roots. So in general, what's the definition of a root? So the root of a function is what? Where x equals 0. Is that right? Root of a function is just where x equals 0. When y is 0, we better know. Which is it? There are values, any value of x that does what? Makes y 0. The output is 0. Okay? So values of x, so it's the same thing with rational functions. Values of x that make y equal to 0. So now we look at the structure of a rational function. How do we get this thing to be 0? How do we get a value of x that makes that 0? What will make what value of x? How can we be more specific? Okay? So now we want to talk in terms of n and d. So what values of x will make r equal to 0? Fernando.
You would set the d of x equal to 0.
D. So when d is 0, then the whole thing is 0. What do you think? What happens when d is 0? You can't do it, right? It's only shoot. What were you gonna say? Question. What's that? So you think when n is 0. So let's go back to when d is 0. Can d be 0? No, not unless you're Chuck Norris. So Chuck Norris, d can be 0. It's no problem. You can do it. But the rest of us, no, you can't divide by 0. Okay? Did you hear that long ago, Chuck Norris and Superman, they fought it out? Did you hear this? Did you know this? Jackson, are you embarrassed?
No.
So Superman and Chuck Norris fought it out, and they agreed that the loser would have to wear his underwear over his pants. Okay? Okay, so d cannot be 0. So what values of x make this whole thing 0? Taylor. You said it. Yeah, so when you have 0 divided by anything except 0, so 0 divided by any non-zero number makes the whole thing 0. So the roots of a rational function, the roots of r, we're going to find by are the roots of n. What are the values of x that make the numerator 0? That will make the whole fraction 0. Okay? Very, very common mistake is students will take all the roots of n and they take all the roots of d, and they say these are all the roots of r. Don't do that. The roots of d are not roots of r. Roots of r are values of x that make that fraction 0. It's only the roots of n. It's only the zeros of n that will make the fraction 0, not the zeros of d. But the zeros of d are important. Okay? So for another reason. They're where the function is undefined. Okay? What about the y-intercept? So what about the y-intercept of a rational function? How would you find its y-intercept? Set x equal to 0. What do you think? Yeah, just the same as a polynomial. We want to know what's the y value when x is 0. So you just plug 0 into your function to see what you get for y value. So y-intercept, no different. Okay? The roots of a rational function, the roots of the numerator. Okay? So now we want to investigate this idea of how this denominator, what role does it play in these rational functions? So open up to page 222. Okay, let's talk this, before I take attendance, let's talk this through. So you got 5 gallons of liquid flavoring to make some drink mix. Okay, so this is like the sugar. This is the syrup, okay? This is syrup. It's always 5 gallons. It's always 5 gallons of syrup, okay? The water will be added to the vat and mixed with the flavoring to produce the drink. So suppose the water is added until the total mixture is 7. What is the ratio of flavoring to water? So when you go through this, you've got 4 quantities to keep track of. First one is the amount of flavoring. How much? Always 5, never changes. What's the next quantity we're going to keep track of? How much water? What's the next quantity you got to keep track of? Total gallons of both. And then finally, the ratio of syrup to water, flavoring to water. Okay, so as you're working through these questions, all 4 of those quantities are in play. And you got to go slow for each one. Keep track of those 4 things as you work this out. And then, yeah, so work through number 2 as I take roll. Any questions on the setup? Okay, go. Okay. Ratio, so 7 gallons of total. What's the ratio of flavoring to water? Michelle, you're up. For part A, yeah. So the ratio of flavoring to water, you're saying it should be what to what? 5 to 7. What do you think? Christian Kiefer, agree with that?
Yes.
Patrick, agree with that?
No.
Tell me.
That is 7 is the total mixture.
Okay.
And it's the ratio of flavor to water.
Okay, can I have your attention up? Let's give Patrick your attention. Go ahead.
The ratio would be 5 to 2.
5 to 2. Where does the 2 come from?
The total mixture is 7 minus 5 flavor.
Yeah. Okay, so that's what it is. It's flavoring to water, not flavoring to total, right? So it's 5 halves, or 2.5. What does that number tell us? The 2.5. What is it telling us? Yeah, Adam.
That means for inside every ounce, every gallon of water that we use is an extra 2.5 gallons of flavoring.
For every gallon of water, there's 2.5 times. So for every amount of water, there's 2.5 times as much flavoring. Is that right? Yeah. So it's like this, the amount of flavoring relative to how much water we have. You see? It's the amount of flavoring relative to how much water. This is saying there's 2.5 times as much flavoring as water. Okay? 18. Ali. Where's Ali? There you are. Sorry. Where's the 11? 5 over. What's the total? 18. So how much water? No, so we don't have a total of 7 anymore. So we have the 18 minus the 5 of the flavoring. So it's 5 over 13. Okay, and so again, that ratio means how many times more flavoring than we have in water. Okay, the function, now here's the important thing. So the function is, what's the input into that function? So f of x, what is x? Isn't that the total volume of both? And the output is what? The ratio of how much flavoring? And how much water? If the total is x, the input is x, then how much water do we have? X minus 5. And this gives us how much more times flavoring we have than water. Or the relative amount, the amount of flavoring relative to how much water we have. Questions on that so far? Okay, so this notation right here means x approaches 5 from the right. X approaches 5 from the right, meaning values greater than 5 decreasing towards 5. So x approaches 5 from the right. Or in other words, values greater than 5 decreasing towards 5. So let's make a sequence that represents that. So this, all right, let's do that over here. So what's a sequence of values greater than 5 that decrease and get closer and closer to 5? So we could start with, sure, 10, okay? And then we want to get closer to 5. What should we do next? 6. Then what? Let's get there a little faster. 5.5, how about? Then 5.1, 5.01, and let's get really, really close. 5.00001, how about? This is the idea. This sequence of x's is the idea of x approaches 5 from the right. Numbers greater than 5, getting closer to, decreasing and getting closer to 5. So what we want to analyze then is in our function, what is our output of our function as x approaches 5 from the right? So we're going to plug in these x's and get out what that ratio of flavoring to water is. So quick, can we do this rapid fire? So if it's 10, is it 1? 1-to-1 ratio. That means for every part water, we have the same amount of flavoring. How about when it's 6? What's the ratio? 5. Meaning? What does it mean? If that number is 5? Five times more flavoring than water. 5 times more flavoring there. So what about 5.5? Is that 10? Help me here. We want to get out early today, so help me out. Is this 10? 5.1. So let's write the function here. 5 over x minus 5. Is that 50? That's 50. 5.01. 500. So what does that number 500 mean? And why does it make sense? Tell the person next to you. What does the number 500 mean? And why does it make sense when the input is 5.01? Go. Austin, you're up. Give it a shot. What does the number 500 mean, and why does it make sense when the input is 5.01? Oh no, okay. There is Ryan. Tell me. Yeah. What does the 500 mean, and why does it make sense that it's 500 when the input is 5.01 in the context of water and flavoring and ratios? What does the number 500 mean? Okay. Justin P. What does 500 mean in this situation? What does that number mean? Yeah? So in terms of the flavoring in the water, what does it mean? Scott's on the edge of his seat. Scott.
Is it the ratio of flavoring the water in decimal form? So it'd be like 400% of flavoring the water?
Okay. So yeah, what does that number mean? 500.
Flavoring is 500 times greater than the amount of water.
Yeah, the amount of flavoring is 500 times greater than the amount of water. And why does that make sense when the input is 5.01? Jackson.
Because that's how much water you have. Like, you're only getting 0.0001 parts of water.
No, we're here at 500.
Okay, so it's 0.01 part of water. So that would be like, you could say that as like gallons, that's 0.01 gallons.
Versus?
Versus the amount that you need to have a total of.
0.01 water versus how much flavoring? 5 flavors. So 0.01 water is it's 1/500th of now your 5 gallons of the flavoring. Okay, so that ratio is telling us how many times more flavoring we have than water. And so as you get closer and closer to 5, what happens to that amount of water? Decreases, right? It decreases, and therefore the ratio of flavoring to water does what? Increases way up. Anyone get this last one? How many zeros? 500,000? So as x approaches 5 from the right, what does the output of this function do? So we could keep making smaller and smaller, closer and closer to 5, meaning less and less water relative to that 5 gallons. And what's the output going to do? Yeah, it's going to go up without bound. It's going to go up as high as we want, just as long as you put a small enough amount of water in, so that total is close enough to 5, that ratio is going to go way up. So let's see what that looks like on a graph. So if we were to graph that, here's 5, okay? And what are we doing? We're approaching, this is the idea of approaching 5 from the right. X approaches 5 from the right. We picked our numbers getting closer to 5, decreasing and getting closer to 5. And what happened to our output? It gets as large as you want it to get, just as long as you get close enough to 5. Put a small enough amount of water in, and you get a big enough ratio, as big as you want, okay? So this is the idea of what's called a vertical asymptote. It's an imaginary vertical line that signifies that output is going to get as large as you want. So it's like it increases without bound. And in this case, that ratio increases without bound as x approaches 5 from the right. What about as x approaches 5 from the left? Even though that doesn't make sense in this situation, we can still talk about the function. So what, those numbers will be negative, right? So if you have negative values, and they're going to get very, very large negatives. So x approaching 5 from the left will look like that. Okay? So this is typical behavior at what's called a vertical asymptote. Your output gets large, and so why is it doing that relative to the function? So we got the f of x is 5 over x minus 5. So notice it's like we're trying to make that denominator 0. As x approaches 5 from the left to the right, this is getting closer and closer to 0. And so that ratio gets larger and larger and larger, whether positive or negative. So the denominator, the roots of the denominator give us the vertical asymptotes. And so what is our vertical asymptote? X equals 5. Roots of d of x give vertical, what's called vertical asymptotes. What are the roots of this function, f of x? What are the roots? What's that? Why not, G? Exactly. So yeah, there's no way that 5 could be equal to 0. So there's no x value that can change that 5 into a 0, and that's what the roots are of a rational function. Values of x that make the numerator 0. So this has no, f of x has no roots. Which means that what about the graph? Never, and it's never going to touch across the x-axis. Okay, so this has no roots. We have a vertical asymptote at 5. What about y-intercept? What will the y-intercept of this function be? Yeah. Do it. What do you get? What's the y-intercept? -1. Plug in f of 0, right? Plug in 0 for x. Zero, -1 is the y-intercept. Even though so everything to the left of 5 in the context doesn't make sense. But just looking at this function 5 over x minus 5, we can just assume values of x less than 5. But with the drink context, this function, it only makes sense here because you can't, if you've got 5 gallons of flavoring, you can't have less than 5 total, right? So only the red makes sense in number 2, but just as a function, 5 over x minus 5, we could also look at what's happening over here. Okay, questions on that? Yeah?
Why does 5 have like power of plus? The question.
The plus is from the right. So this right here would mean, I think you're talking about this right here?
Yeah.
Yeah, so if we were to take values of x getting closer to 5 from the left, it would be x approaches 5 from the left. And that would be a sequence like this: 4, 4.5, 4.9, 4.99, 4.9999999. So this would be like x approaching 5 from the left. So it would be x arrow 5 minus. Okay? Other questions? Okay, so we've got almost everything we need for rational functions. So let's just practice a little bit here. If you go flip a page over to that one. What's this? Number 6. A through D. Find the roots, the vertical asymptotes, and the y-intercepts. Go. A through D. So for each one, you're going to do the roots, the vertical asymptotes, and the y-intercept. For all 4. Move quick. Be efficient. Shouldn't you be using a calculator for this? Everything is done by hand, and you can do it. You should be done with A and B by now, so you can check your answers. I put the answers up for A and B, check your answers, and then cruise forward on C and D. Got questions, man? Come around. E? Yeah, that's what I'm doing. Yeah. An A? Yeah. How do you, the y-intercept?
Because you said it's 0.
Right. It's the value of y when x is 0.
I wrote down
Okay. Yeah, isn't that, yeah. Okay, so to get the roots, where am I looking here for part C? What do I look at to get the roots? Angelica? How am I going to handle that? I'm going to get the roots. How am I going to handle that? Okay, keep going. Okay.
No, I'm sorry. You can distribute out to 6. Put 6 parentheses, x squared minus 4. And from there, you can factor that out. So x plus 2 and x minus 2.
Good. So yeah, you got to know your factoring for these rational functions so you can get the factored form to get either the roots or the vertical asymptotes. So our roots are at?
2 and negative 2.
That's right. Vertical asymptotes of this one. Where we get 0 in the denominator. So x equals 3, x equals negative 1. The roots of the denominator are the vertical asymptotes. They're not roots of the function. That's what students want to do all the time. They want to make the roots of the denominator roots of the function. They're not. They're undefined there. So it's like the furthest possible thing from a root. There's not even a value. Okay? Y-intercept of this one. Plug in 0. What do you get? Negative 24 divided by? Negative 6? 4? 0, 4. Questions on part C? Okay, so I'm going to, just for time's sake, so quickly, I'll just write this down. What are the roots of D? Negative 3. Vertical asymptotes, you're going to have to factor that. So you got it. That's from a previous knowledge, previous course. X plus 5, x minus 1. Should be easy. So therefore, the vertical asymptotes are negative 5 and 1. Y-intercept 3 over negative 5, or 0, negative 3/5. Questions on D? It's basically you just know where you get your roots, know where you get your vertical asymptotes, know how to do factoring in algebra. Okay? Know how to do factoring and plugging in. So let's talk about C. We're going to do C. There's only one thing left we have to talk about to kind of put this all together and come up with a graph for that. So that's not a simple graph. That's complicated, but we've got all these pieces that we're understanding. So all we have left is end behavior. Okay? So let's talk about end behavior. of these rational functions. How did we get end behavior for the polynomials?
Highest power, higher power.
Leading term, right? So there's no leading term per se. There's no, because it's two polynomials in a fraction, right? So, but the principle is the same. We're going to get x, as x gets really, really large, what's just the numerator going to be like? What are we going to focus on as x gets large? What are we going to focus on the numerator? The leading term of the numerator, right? And as x gets really, really large, what are we going to focus on the denominator? The leading term. So as x gets really, really large, h is virtually going to be like the ratio of 6x squared to 2x squared. The ratio of the leading terms. So what we get when we simplify that is what we call, so this just simplifies to 3. And so this isn't the leading term because h doesn't really have a leading term, but in effect it is. In effect, this has the effect of the leading term of the whole fraction. So we call it the effective leading term. So you get the leading term of the numerator, the leading term of the denominator, and you simplify that. And that result is, in effect, that's the leading term of h. So what happens when x gets really, really big positive? What's y going to do? It's going to be like what? 3. And when x gets really, really big negative, what's y going to be like? So before we said, does it go up or does it go down? We said, does y go up to positive infinity or down to negative? Up to positive, down to negative. But now with rational functions, it can do other things. For instance, this. So as x gets really, really large, the function's going to behave like 3. What is 3 like? A graph of 3. Yeah, horizontal line at 3. So when we get way out to the ends of this function, it's going to turn into just like kind of very close to a horizontal line at 3. So now we've got everything. We're going to put everything together. And we're going to sketch the graph. Here we go. What was our y-intercept again? 4? 0, 4. Great. Okay, so first of all, roots. What were the roots? 2 and negative 2. Same thing as before with polynomials. That's the x-intercepts. Okay? Vertical asymptotes. 3 and negative 1. So we have an imaginary line that this graph will not cross, but as it gets close, the y values will get very large, either positive or negative. Okay? Y-intercept. 4. And end behavior. So at the end, so when x gets really, really large, what's it going to be like? What's y going to be like, the graph? 3. And when y gets very, very large, negative, it's just going to be like 3. But we don't, not in the middle. Just the end behavior. So we don't care about this 3 in the middle. It's just when we get way out to the ends, we know that graph is going to approach 3. Okay, so we start putting this together here. We know we got this, let's start here. We got this root here, and we've got this y-intercept here. So maybe, so they're going to connect like this. Okay? Now, what was the multiplicity? Multiplicities apply too. What was the multiplicity of our x minus 2 factor here? This is 6 times x plus 2, x minus 2, right? What's the multiplicity on x minus 2? 1. So it's going to do the same thing the polynomial does. It's going to go right through like a line. So as we get close to this vertical asymptote, we'll go up to positive infinity or down to negative? It's got to go to negative because it's not going to, it can't cross here anymore. There's no root here. So it's got to go to negative infinity. And you can check that by just plugging in, say, 2.9. You should get a large negative number.
How are they going to connect?
What's that?
How are they going to connect the negative 2?
They don't, because whenever there's a vertical asymptote, there's a break. They don't connect. All right, so now, same thing here. There's no root here. So as we get closer to this asymptote at negative 1, is this going to go up to positive or down to negative? It's got to go up to positive. Like that. Okay? And so We know we're going to be close to 3 here at the ends. So then what's this going to do? Is it can't cross anywhere here, but it's got to cross there. Is it going to go straight through? What's the multiplicity on x plus 2? 1 again, so it's going to go straight through. Down to negative or up to positive infinity? There's no root here. It can't come across again, so it's got to go down to negative. Last part, so we're here. So here, up to positive or down to negative? No root here. It's got to go up to positive. See how this works? So you're piecing all these pieces together. You're making these like little conclusions based on where the roots are and where there are no roots. That's a big thing. Where you don't have roots, you can't have it crossing the x-axis. Let's see how we did. Turn it on. Okay? So we got it. We got all the elements that we wanted. We got the roots, the asymptotes, the y-intercept. So let's investigate the end behavior here. So when will this graph look like 3? When will it look like 3? When x is really big, positive or negative. So if we zoom out on the x-axis, now we're looking at large values of x, positive and negative. Look at that. It's 3, basically, right? So all that stuff in the middle, between -5 and 5, we can't see that anymore because those are small values of x. For large values of x, this thing is virtually 3 because that's what we got for the end behavior. Zoom back in again. And now you start to see what's happening in the middle at the roots and the y-intercept and the asymptotes.
Does it ever actually get 3, or is it just getting closer?
Yeah, it gets very as close as you want to 3. As close as you want to 3 so that it's indistinguishable from 3. Anybody have a question? Have a great weekend. Look for homework on Blackboard. And look for test results.